Okay, so Bismillah Rahman Rahim. Now we discuss this critical depth in non-rectangular channels. So with reference to this figure, for non-rectangular channels, we defined the Froude number that is equal to V velocity divided by square root of G into YH. G into YH. Clear? Now this YH is the hydraulic depth. This is YH. So this is the hydraulic depth, which is defined as the flow area divided by the top width. So this is the flow area, cross-sectional flow area. And this is the top width as shown in the figure. Width of flow area at the water surface. This is the top width of the flow area. Now in this case, what we do, since we have to consider now the total discharge, so we already know that this V, that is equal to capital Q divided by the area A, discharge by area A. Now this can be written as this Froude number, it can be written as Q divided by square root of G into A cube divided by T, or this is equal to Q into square root of T can go up, divided by G into this area A cube. Now for irregular shape flow section of area A carrying a discharge Q, we can write down the specific energy. So the specific energy, that will be equal to the depth of flow plus the velocity head divided by 2G. Now in terms of the discharge, this will be equal to Y plus we have Q square divided by 2G into A square. Now what we have to do is that we have to differentiate this with respect to Y, the depth of flow, and setting to 0 to find the YC. Now we want to calculate the critical depth. So we have to differentiate this equation with respect to Y and setting to 0. So in order to find YC, that is the critical depth, that is the value of the depth for which the specific energy is minimum. So what we do is that we differentiate this dE divided by dy. So this will be equal to d divided by dy into y plus q square divided by 2g into a square. So we take the derivative and then equate this to 0. So now when you simplify this here, what we will get is that we will get this a dE divided by a dy when you take the derivative. So this will be equal to 1 minus q square, that is constant, divided by 2g, and this will be equal to 2a 2 divided by a cube into dA by dy, because the flow area, that is a function of the depth, so that's why this will be equal to again dA by dy, and this will be equal to 0. Now this dA is equal to what? Is this dA, now in here this is dA, so this dA, so this will be equal to t times dy. Clear? From here what we can write down is that dA divided by dy, dA divided by dy, that is equal to t. So we can replace this dA by dy with t now. So now what we can write down is that this will be equal to 1 minus q square divided by g into a cube into t, and that is equal to 0. So from here now I just replace this 2 will cancel out, this 2 will cancel out with this 2, so q square by g a cube into t. So this is what is written here, q square divided by g into a cube, and this whole multiplied by t, the top width. So this is equal to 0. And then from here what we can simplify is that this q square divided by g, this will be equal to a cube divided by the top width, and this is actually the condition that is corresponding to the critical depth, means that this is equal to y is equal to yc, the critical depth. Clear? So this is the important equation. Clear? This q square by g into a cube divided by t, this equation A must be satisfied for critical flow, because we differentiated this dE by dy to find yc. So that's why this equation here, this equation A, this must be satisfied for the critical flow conditions. Now in this case, in this equation A, for the given cross section, this right hand side of the equation, this is a function of y only. This is a function of y only. So now the thing is that we generally need a trial and error solution to find yc, because you have numerator and denominator, and this for a given cross section, this right hand side of equation A, that is a function of the depth only. So we generally need a trial and error solution to find yc. Clear? Now in this case, for vc, the critical velocity, we have this vc, the critical velocity. So this will be equal to, or this discharge, that will be equal to the critical velocity multiplied by the area. Q is equal to A into V. So we have VC into AC. So now when you put this in the above equation, so this equation then becomes, from here you just put in this equation, so this equation then becomes VC square divided by G equal to AC by critical flow area divided by the critical top width. This you put here. This in the equation you can put. So we will get this equation in terms of the velocity. Now you see here that this equation VC, so this is equal to square root of G into AC divided by TC. AC divided by TC. And what is this area divided by TC? This is actually your hydraulic depth. You see here YH is equal to A divided by T. So this is actually your hydraulic depth. So this can be written as square root of G into YH. This is the hydraulic depth, and because this is AC by TC, so that is corresponding to the critical depth. Clear? This is the equation. Now in this equation, VC divided by square root of GYH into C, this will be equal to 1, and that is the Froude number. Clear? So again, for critical flow, the Froude number is 1. We defined the Froude number, that is equal to V divided by square root of G into YH. So this is what you get. VC divided by D square root of G into YH, and this right hand side will be 1. So that is for critical flow. So you can see again here that for critical flow, the Froude number is equal to 1. Now for rectangular channel, if you simplify, you will get the same result. This is for non-rectangular channel. So for rectangular channel, if you simplify the above equation, equation B for rectangular channel, so what we have is that in that case, EAC, this critical flow area, so that will be equal to the top width TC into the depth YC. It will be equal to this. Why? Because for rectangular channel, if we have a rectangular channel, so in that case the width of the channel and the top width, they are the same. This is Y, so this is T, we denote by T. In your book it is capital B, but we denote it by T, and this is the width, small b here. So you can see for rectangular channel, this T and B, they are the same. So that's why B into Y or T into Y is your area. Clear? So now when you put this, so in this equation, if you put that, so we say that VC, that is equal to square root of G, and now instead of AC here, we put TC into YC. So this is TC into YC divided by TC. So now this cancel out TC with TC, and we are left with square root of GYC. This was the condition that we obtained for critical flow. Clear? Now in case of open channels, so the most commonly encountered shapes that are either we have partially full circular sections or we have the trapezoidal section. So for if we have trapezoidal section, when we solve the problems, this equation will help you for trapezoidal sections. For trapezoidal cross section, So we have this equation, Q square by G is coming here from equation A, Q square by G, and this will be equal to the area. So we have this area B into YC B into YC plus M is the slope, M ratio 1, M into YC square, the critical depth, and this is whole power cube. You can see here in equation A, it is A cube, and then divided by the top width. So the top width, that is equal to B plus 2 times M into YC. So this is the equation that we can use for the trapezoidal cross section. Here in equation A, we just put the values. So the basic concepts that we develop for rectangular channel, now we can generalize in this topic for non-rectangular channels. So if the problems are given for non-rectangular channels, then these equations we can apply to analyze the problems. The next topic in our textbook, that is the occurrence of critical depth. So now in the critical depth, when the flow changes from subcritical to supercritical or from supercritical to subcritical, the depth must pass through critical depth. You can see here in this example here that the flow changes from subcritical to supercritical. So it passes because of the change of the slope. This is how the type of flow changes. So when the flow changes from subcritical, why it is subcritical? Because this dash line, it represents the critical depth. This represents the critical depth. Now Y1, it is above the critical depth, so we have the subcritical flow condition. You see the slope which is less than the critical slope. So this is the mild slope, as we already discussed. This is the mild slope. This is known as the mild slope. When this changes to a steep slope, you see here the slope S0 is greater than SC. So this is actually steep slope condition. This is the steep slope. So it passes through the critical depth. Why steep slope? Because now you see the critical depth, it is above the water surface. So the depth of flow, it is less than the critical depth. That's why we have this supercritical flow. So this figure is from our textbook. They say that when the flow changes from subcritical to supercritical, it passes through this critical depth. And this is also the situation that when we have supercritical flow, when we have a situation where you have supercritical flow and it changes to subcritical flow, so it will pass through the critical depth. It will be somewhere here. So this critical depth occurs. Clear? Now in this case, in the subcritical situation, this is given as the subcritical situation. At the break of a slope, this critical depth occurs. This is known as control section. This is known as control section. We will discuss about this control section in the next lecture when we discuss about the flow measurement devices in open channels flow. So this we will discuss in detail, that what is a control section, what is the advantage of this. So in here, this is known as the control section. Clear? And a similar situation occurs when water from a reservoir enters a canal. So we have this reservoir here, and from this reservoir the water enters into the canal. So what happened in the canal, you can see that the depth of water, it is less than the critical depth, so we have supercritical flow in this canal. So when the water enters into the canal, again we have this critical depth which is here. Clear? So therefore this section here where the critical depth occur, this is known as control section. We will study that why it is called control section, because it controls the water upstream. Control section. Clear? So by measuring the depth at a control section, we can compute a reasonably accurate value of discharge. Just like we studied for rectangular channel, that the discharge that is equal to square root of GYC cube. This equation we studied, or the equation that we just developed here, this equation here. Clear? So when we have the critical situation, you see at y is equal to yc, so we can calculate the discharge. Clear? Rectangular channel, this is for rectangular channel, and for non-rectangular channel that we just studied. Now at a control section, there is a specific relationship between the depth of flow and the discharge, regardless of the channel roughness and slope. So this means that these are desirable locations for gauging stations. It means that these control sections here, these are desirable sites, locations for gauging stations. We will study this in detail in the next lecture when we study flow measurement devices, that how they are used as the gauging station, means we are using it for measurement purposes, because for a control section there is a specific relationship between the depth of flow and the discharge. Clear? Now it also means that when the upstream and downstream flow conditions change, the transition of such changes through a control section are restricted. Clear? They are restricted. Now this control section, remember this critical depth, because you see here in this example or in this example, so this critical depth creates a control section, which we call it as a control section. Clear? But this is not the only means. Control structures such as the sluice gates and orifices may also be used to create control section. Just like you see, I show you the diagram of a dimensionless curve. So there a critical depth establishes over the wear, right? So control structures such as the sluice gates and orifices, they can also be used to establish this control section. Clear? So we are interested in this control section when we are, for example, calculating discharge accurately. Clear? So this we will study in detail in the next lecture which is coming, where we will study the flow measurement devices. But here we are discussing the occurrence of the critical depth. So this is how the critical depth occurs. These two examples, they are given in your textbook. Now to continue with this, so you see this is another example. Now in this case, again we have the mild slope, because S0 that is less than the critical slope. So in this case, you can see that the critical depth occurs. This we have free overfall. This is free overfall. Clear? Now we have a subcritical flow. As I said, that we have the mild slope. So friction produces a constant decrease in energy in the direction of flow. We already studied that when we consider the fluid friction, so there will be a constant decrease of energy in the direction of flow. So it is obvious that at the point of overfall, this is the point of overfall here, this is the point of overfall. Clear? The total energy must be less than at any other point upstream, because we say that when the water flows in this direction here, so when the water flows and because of the friction there is a constant decrease in the energy, so we expect that the energy at this point here must be less than at any other point upstream. So A's critical depth is the value for which the specific energy is minimum. We would expect critical depth to occur at here. Because what we studied that the critical depth has the minimum specific energy. So we would expect that the critical depth occurs here. Because here we say that because the energy should be minimum here as per what we assume that when we have a friction, so in the direction of flow the energy decreases, so we expect here to be the minimum energy. And when we say the minimum energy, we already studied from specific energy diagram that that is corresponding to the critical depth. So it means that the critical depth should be here. Clear? But now in this diagram, we see that the critical depth does not occur here. The depth here is less than the critical depth. The critical depth is here. Now what is the reason? You see here, this is now the critical depth. This is YC. So now this critical depth, it occurs 3 to 10 times the YC upstream of this brink of the overfall. Clear? Now, what is the reason? The reason is that when we, for the value of critical depth that we derive on the assumption that the water is flowing in straight lines. When we develop or calculate this critical depth, it is on the assumption that the water flows in straight lines. But now in here, there is a curvature. You see here, there is a curvature due to this overfall. So it means we are deviating from the assumption. That's why the critical depth does not occur here, but it occurs here. Clear? So in the free overfall, this is the free overfall, the gravity creates a curvature of the streamlines with the result that the depth at the brink, this is the brink here, is less than the critical depth. So because of the curvature of the lines, the depth at the brink is less than the critical depth. See, the critical depth is this dash dash line. Clear? Now this YB, what is the depth? This YB is approximately equal to 0.72 times YC. This is actually coming from experiments. In experiments, we have found that the depth of water at the brink, this is the brink here, this is equal to 0.72 times the critical depth. And the critical depth generally occurs 3 to 10 times the YC upstream from this brink. Clear? Now, if the flow is supercritical, this is for subcritical here. Now, if the flow is supercritical, we have the steep slope, S naught is greater than SC. So if the flow is supercritical, there is no drawdown. You can see here, there is a drawdown, but when we see a steep slope, there is no drawdown. You see throughout the depth is less than the critical depth. So you can read the detail in your textbook. So if the flow is supercritical, there is no drawdown as shown here. So this is a few examples where we discuss the occurrence of the critical depth is given in your textbook. Clear? There can be many other situations where we can see the occurrence of this critical depth that we will discuss as we study more topics. Now the next thing is this humps and contractions. This is the next topic in your textbook. So we already discussed some of the applications of the specific energy. So if you remember, we consider when we have a fall in the channel bed, when we have a rise in the channel bed and the flow is subcritical or supercritical. So actually we discuss all these things. Let us continue with that discussion here. In this case, for first we will discuss the humps and then I will come back to the contractions. So in that case, now we see that how the specific energy, it helps us to visualize and understand the analysis of these problems. Clear? So now in this case, what you see here is that we have remember in this we discussed for subcritical flow. So the depth is greater than the critical depth over a hump. Clear? So this we call it as hump. Maybe in some books it will be written bump. So these are just similar words that are used to denote for this. We have a bump, or this hump is written, or a step. Clear? A step is provided. So these are similar names. Now in this case, you see that when we have subcritical flow, in this case now delta Z is very, very small. So we already discussed this, if you remember from the previous lecture, that when the water flows over this hump, so there is a decrease in the specific energy. This is what we discussed in the towards the last of the previous lecture. In the end, this is what we discussed, that when we have subcritical flow and this is the hump is introduced, the bed of the channel, it is raised, but it is very, very small. What will happen, that the water surface, it will depress. You can see here there is a, why it will depress, because there is a decrease in the specific energy. The hump, this hump causes a drop in the specific energy. Clear? So is the specific energy decrease and the discharge is the same. Remember here it is written that the flow rate is the same in all the 4 cases. We are not going to change the discharge is the same. So it means that when the specific energy decreases, so the discharge is the same, then it must be followed by a decrease in the depth. Clear? So that's why you see here that there is a depression in the water surface. Now in this case delta Z is very, very small. Now when we increase the height of the hump, so there is a further depression. You can see here this is increasing. Because of increasing this, the specific energy is decreasing. So this is accompanied by a decrease in the depth. Now when the height of the hump, that is equal to the critical hump height. So this delta Z critical, this is known as the critical hump height. What is the critical hump height? It is the depth of the hump which will cause the critical depth to occur, which will establish the critical depth over the surface. This is actually what? This is YC. You see this depth is decreasing. Originally it is a subcritical, above the critical, but now the depth is decreasing because of increasing the height. So this delta Z critical, this is the critical, that height of the hump which will cause the depth here to be YC, the critical depth. That is known as the critical hump height. Clear? This is the minimum height of the hump that causes critical depth. So the critical hump height. Now in this case, what is happening? This YC, because now it is critical, so we have critical depth occur here. This is the minimum energy. If I go back to the specific energy concept, what we studied here in the specific energy concept, we have this Y, and for a given discharge, we have this curve here, and this is the specific energy E. So now the critical depth comes. The depth is decreasing. You see here the depth is decreasing from here, and now this is YC. So this YC, for this YC, we have this E minimum. This is the energy, because the water should have the energy to flow. So now the critical depth has occurred, and for the flow to be the same, this is the minimum energy required. This is the minimum energy required to cause the flow. Now when we further increase the height of the hump, you can see here that in this case, we further increase the height of the hump above now the critical. So what will happen? That this critical depth will be maintained. When we have the subcritical flow, this critical depth will be maintained here. It is not going to change. But now what will happen? This obstacle is increasing. So now the water needs energy to flow over this hump. And since we have YC, this is the minimum, the depth is corresponding to the minimum specific energy. So now what will happen, that you keep on increasing this hump height above the critical hump height. What will happen? The water needs energy to flow over it. So in order to do that, what will happen? It will increase in depth upstream. You see here it has increased. Previously this was the hump height. This is the depth of water upstream of this hump. But now the water depth has increased. Clear? So what will happen is that when we increase the hump height, the depth upstream of the hump increases. Clear? Because it want to gain the energy. You will see here the depth has increased. Now it means that the specific energy has increased. So it needs more energy in order to overcome this obstacle, which is the hump. So this effect, this phenomena, the depth which increases, so this effect, this is known as a damming action. This is written in your book. Like dam, the water level will rise. Clear? When we construct a dam, the water level is stored, water is stored behind the dam, the water level rises. So that's why this is known as a damming action. This is known as a damming action. Let me write down this damming action. So with damming action, immediately downstream of YC, the flow must be supercritical. This we will discuss in detail. It says that now you see here, this because of damming action, we have this YC. We will solve a problem on this. They say that the depth here must be supercritical, and then there will be a hydraulic jump, and then it will establish the normal depth, and the water will continue. So it means that the depth then immediately downstream must be the supercritical depth. It cannot be the subcritical depth. We will solve a problem on this, that what is the reason. This is the problem which we will discuss to further highlight. Because if we have immediately after YC, again we have the subcritical depth, then this is not possible, because there will be then no way of dissipation of the energy. So we need to dissipate the energy. So this depth has to be the supercritical, and then it passes through the critical depth and becomes a subcritical depth. So actually this situation, you will see that this is the hump, that it has a flat top. This becomes a broad crusted weir, and this is what you saw. You see in the broad crusted weir, when we operate the gate, you see we have the critical depth, and before that we have what? We have the subcritical depth, and immediately after the gate it was a supercritical depth. So this is what we already observed. So this we will see when we solve a problem, and also we will study the broad crusted weir in the coming lecture. Clear? So this is the explanation is given in your textbook. You can read about it. Now in this case, this is what I said here. This now I try to explain with reference to the specific energy diagram. So you see here that in this case again we have subcritical flow. So when we have this subcritical flow, why? Because this is E1 here and this is the depth here. So we provide this rise in the bed of the channel. So this is delta ZA. With this delta ZA, what will happen? The flow is subcritical, so there is a depression. You can see here that there is a depression in the water surface. The reason is that when this water flows over the step or the rise, clear, there will be decrease in the specific energy. This is what we discussed towards the end of the previous lecture, applications of the specific energy. Clear? You can see here, because this E1 here, this will be equal to delta Z plus E2. So it means that this specific energy, it decreases as the water flows here. So that's why this decrease in E will be accompanied by a decrease in depth when we have the subcritical flow. So now in this case, what is happening? This is the specific energy diagram. So we are here. This is Y1 here. This is your Y1, the subcritical flow. Why it is subcritical? Because the critical depth is here. So this y1 is well above the critical depth. That's why we say that it is the subcritical. Now when we have this delta z for the A case, here you increase, just like we here goes side by side. We increase, then we come to the further increase, and then further increase here for considering the critical condition. Now you see here, in the first case we just increase. So what happened is that there is a decrease in the specific energy. This is what I say. So we are here actually. Now this is the depth, and this comes here, and this is the line here, and this is your E1. This is your E1, which is here. This is your E1 here. This is E1. Now, because as I say that there is a decrease in the specific energy, so that's why we go to the left. We go to the left of this curve. By how much? By this delta ZA. So with this delta ZA, we go to the left of here. We have this 2E2A for case A. This 2A for case A. We come here, and now in here, you see that this is now the depth Y2A, which is still subcritical. Which is still subcritical here. For this specific energy, this is also the possible depth. This is also the possible depth. But if this depth has to be corrected, then this depth has to pass below the critical depth, and if it flows like this, then in that case, this will be the correct depth. But since it does not pass through the critical depth to become the supercritical depth, that's why in this diagram here, this is incorrect. This is incorrect. Clear? So that's why the flow still remains as subcritical, and this is the Y2A is the correct depth. Now what we do is that we further decrease. In case B, we further decrease the specific energy by increasing this here. You see that delta ZB, it is greater than delta ZA. This is more. So what will happen is that in this case, there will be further decrease in the specific energy. You see, essentially, we are bringing the specific energy to the minimum where we have the critical depth. So it means we are decreasing the specific energy unless we come to the E minimum. So you can see here that it will further decrease this specific energy. So for delta ZB here, we come from here to here. So now this is E2B. For case B, this is E2B, and this here, this is now the depth. Still it is subcritical. So this Y2B, this is still the subcritical depth. It does not pass through the critical depth. So that's why this depth here, this is not possible. So that's why the flow is still subcritical. Now in the third case, what we do is that we come to part C, and now we increase this delta Z to become the critical. So when we have this critical situation here, now you see that E2, it is reduced to E minimum, the minimum specific energy. So in this case here, so whose mic was on? Okay, now in this case you can see that we have this E minimum. So in this E minimum here, E2 is equal to E minimum. So in this case, we are coming to this delta ZC. So in this delta ZC, we are reducing now, the specific energy is reduced to the minimum. So you see in the C case, we have reduced the specific energy to the minimum. We are coming here. So that's why you see that the critical depth that is established over this step, the critical depth. So the critical depth that is established here. Now this is the minimum energy. You see the water needs energy to flow. So the water energy has come to the minimum. That's why the critical depth has established. So now for this critical condition, this is the value of YC. Now in this D, this is here. I'm talking about here. We come to D. In D, what we did is, let me remove this. Actually, this is here. This is what I discussed. This is for E2 is equal to E minimum. So now in this case, when you further increase, now this delta ZD is greater than the critical height. This is greater than the critical height. This is what we discuss here. This is now the situation. We come to the D, that now you further increase the height more than the critical. So now in this case, when you further increase it, so what will happen is that if you look to this diagram, what you see here in this diagram, when you further increase it, so where we reach here, that your delta Z, it is here. You are coming here. This is the point. So this E2D, this is reduced. You see, it is less than the E minimum. The E minimum is the energy that is required to cause the flow. Greater than the energy, the water can flow without any problem. But now you see that because of the increasing this height so much, that you see that now E2D is this much. Because this water needs to flow, so that's why it should gain the energy upstream. It should gain the energy and then it will be able to flow over this. For this reason, what happens is that the energy increases from E1 to E1 dash. The energy should increase from E1 to E1 dash. Then in that case, it will be able to flow over this hump, and still the depth will be YC. And this increase in the specific energy upstream can occur. This is due to the damming action. This is due to the damming action, that behind this the water level should rise. So when this water, it gains sufficient energy, then it will be able to flow over this step. Now when we consider the contractions, so the contraction is the reduction of width of channel. In contraction, this is the reduction of the width of channel. This is now the top view. So it is like this. We have this as the rectangular channel, and then we have this as the channel width. So this width here, from here to here, this is B, as given in this diagram here. This is B, and then the width of the channel is reduced. So this width of the channel, it is now B1. This is now B1. Now in the humps, we actually raise the bed of the channel. As you saw the different cases, but then when we consider the contraction, so in this case, we reduce the width of the channel. Now when you reduce the width of the channel, what will happen? By reducing the width of the channel, E will not change. E will remain the same. Q will change. Discharge, this rectangular channel that we consider, so this small q, that is equal to Q by B. Now that this B is reduced, clear? This B is reduced from B to B1. B1 is smaller than B, clear? This B1, it is less than this B. So what will happen? This Q will increase. This Q will increase because discharge is the same. So if you reduce the width per unit, discharge with it should increase because this B is reduced. So it will increase this value. So now we consider the case of a subcritical flow, that when the water flows in the channel, bed but there is a contraction here. Width of the channel is reduced. So what will happen? We have subcritical flow. Why? Because Y1 is greater than YC. Again, you see a similar situation is observed, that there is a depression in the water surface. Just like the hump, there is a depression in the water surface. So the depth comes from Y1 to Y2, but it is still above the critical depth. To explain this, we have this diagram here. You see that we have this Y1, and now from Y1 we come here. Now this is the discharge. Because we have reduced the width of the channel here, so that's why we have another specific energy curve. Because the discharge per unit width change, there is a shift in the specific energy curve. Because now Q1, this Q1, it is greater than this Q. The unit discharge has increased. Remember, the total discharge is the same. The unit discharge per unit width, that has increased. So that's why you see that if you go down, so this is now the point here, and as I'm saying that the specific energy will be the same in this case. So for both the curves, the specific energy is the same. The discharge has increased, and now from this point here, you come here, and this is the Y2 value. This is that Y2 value. Now you also can see the difference in the critical depth. This is YC and this is YC dash. So in this case, why it has changed? Because YC is a function of Q. You remember this YC that we discussed for a rectangular channel. This is equal to Q square. This is equal to Q square divided by G into power 1 by 3. So because Q change, YC will also change. Q change, YC will also change. So that's why you see that in the width B here we have YC, but because Q change from Q to Q1, that's why you can see that YC dash or YC prime, it has also changed, because it depends on the discharge. And if we have a supercritical flow, in this case D, we see a supercritical flow. Why supercritical flow? Because you can see here Y1, it is less than YC. So there is a slight increase in the water surface from Y1 to Y2 here, but still the flow remains supercritical because it is still less than YC dash. So the flow will still be supercritical, but there is a slight increase in the water surface. So this is how you see that these specific energy concepts, they help us to analyze the flow problems. We will solve a problem in which we will have a hump. You see that in the hump case, here that we discussed, the specific energy changes, but the discharge remains the same. But in case of contraction here, the discharge changes, but the specific energy remains the same. So now if we have a hump, and it is also followed by a contraction, how we solve the problem? Means we combine the two. We combine the hump and it is followed by a contraction. So how we solve the problem? We will solve this and consider this situation in a numerical problem that we will hopefully study in the next lecture. So it will further clarify the concepts that we are trying to learn here. So you can see from these examples that how the specific energy concepts, this help us in analyzing the complex open channel hydraulic problems.